Okay, in today's lecture, we're going to talk about the section 4.6 material on directional derivatives and the gradient of a function. So to introduce this concept, let's review what we've been working with in chapter 4. We've been talking about partial derivatives and some applications of partial derivatives. So let's recall what partial derivatives represent. If we have a function f of two variables, let's say x and y, then the partial derivatives of that function f with respect to x or y represent the rates of change in the function, or the quantity z defined by that function, in the directions of x or y respectively. So that is, the partial derivatives represent the rate of change of our function if we make a change to the variable x only or the variable y only. The other variable we usually hold as a constant for these partial derivatives. So what we're going to consider in this section is the concept of a directional derivative, which is going to describe the rate of change of some function z in the direction of a unit vector u, whose components are a and b. So when we describe a change in x and y at the same time, typically we're going to describe that change making use of a unit vector whose components are, say, a and b. So geometrically, let's look at this problem of finding a directional derivative and what it represents. So let's start by considering a surface S, which would be defined as the graph of some function of two variables x and y. So in my figure below here, I've got my surface shown in blue, and I'm going to choose a point P given by x naught, y naught, z naught, which lies on that surface. So the z coordinate of that point z naught is the value of the function f at some point x naught, y naught in the xy plane. Now, if we were to consider a vertical plane which passes through the point x naught, y naught, z naught, and is specified by the direction of this unit vector u. So what we're talking about here is a point passing through or a plane passing through my point, specified by the direction of this vector u in the xy plane. And this plane is going to intersect my surface in a curve C. So we're looking at some curve C which lies on our surface, and what we're trying to find is the slope of the line which lies tangent to that curve at the point P. This is going to represent the rate of change of my function as we move in the direction of this unit vector u. So here, the tangent line to the curve C passing through that point P would be this tangent line, and I'm trying to find the slope of that tangent line. So this slope is what is called the directional derivative of our function at the point x naught, y naught in the direction of the unit vector u. So the notation that we're using for a directional derivative is the following. It's denoted as capital D with a subscript of u, so u here is the unit vector, of the function f at a point x naught, y naught. And the way that this is defined is in terms of a limit. So let's think about how this could be calculated formally. It's sort of similar to what we saw in Calculus 1 when we were deriving the derivative of a function. So we could take 2 points in the domain of my function, let's say x naught, y naught, and then some other point which lies a distance along the vector u. So it's some scalar multiple of u. Let's say it has a magnitude of h, so that we move h times a units in the x direction, or h times b units in the y direction, since the components of our vector were a and b. So if we look at the point on our curve, which corresponds to this terminal point of my vector u, we get another point on our curve C. And looking at my initial point, x naught, y naught, we get the point P on our surface. So I know how to find the slope of a line through those 2 points. And the slope of this line would be an approximation to the slope of the tangent line that we're after. So to find the slope of that line, well, we would be taking the difference in the values of my function at the point x naught plus AH, y naught plus BH, so that is this point shown in the xy plane, and the value of the function at x naught, y naught. And then we would divide by the length of this vector h that we've moved. And by allowing h to approach 0, we're looking at points on our curve C which lie closer and closer to our original point P, and therefore this slope that we're calculating is approaching the slope of our tangent line as h approaches 0. So as long as this limiting value exists, that's how we're going to define the directional derivative of our function. Now, just as we saw in Calculus 1, the limit definition of a derivative is not a very efficient way to calculate a directional derivative. So instead, we can make use of the following theorem, which gives us a formula for a directional derivative that's much easier to work with. So here's what our theorem says. If we have a differentiable function f of 2 variables x and y, then the directional derivative of our function in the direction of the unit vector u, whose components are a and b, is given by the product of the partial derivative of f with respect to x times a, the first component of my unit vector u, plus the partial derivative of f with respect to y times the second component of our unit vector, which is b. So we can use this formula involving the partial derivatives and the components of our unit vector to calculate our directional derivative more easily. Now, one thing that we have to be a little careful of in making use of this theorem is that the vector, which is giving our direction, must be a unit vector. So here this theorem specifies that the vector u we're working with is a unit vector. So a lot of the examples we'll see the vector which specifies our direction is not always a unit vector. So typically we have to normalize that vector to get a unit vector that we can use with this theorem. So let's look at some examples of calculating directional derivatives. Here we are asked for the directional derivative of x squared sine y at the point -1, 0 in the direction of the vector v given by 2, -1. So here we can see pretty quickly that this vector v is not a unit vector. So our first step in this problem is going to be to find a unit vector which points in the direction of v. And recall, to do that, we could take our vector v and divide through by its magnitude. So here our vector v was 2, -1, and its magnitude is then the sum of the squares of our components, or the square root of 4 plus 1. So the first component of our unit vector is going to be 2 over the square root of 5, and our second component would be -1 over the square root of 5. So typically we want to start by finding a unit vector that will specify our direction. And in order to apply the theorem that we just looked at for a directional derivative, we need to find the partial derivatives of our function. So let's look at the partial derivative of f with respect to x, which is 2x sine of y, and the partial derivative of f with respect to y, which would be x squared times cosine of y. Now we're interested in the directional derivative in this problem at a specific point, at the point -1, 0. So since we're interested in the directional derivative at that point, let's go ahead and evaluate these partial derivatives at the indicated point of interest, -1, 0. So here we find our partial derivative with respect to x is 0, and the partial derivative with respect to y at -1, 0 is 1. So now, using our formula for the directional derivative, we find the derivative of f in the direction of u at the point -1, 0 is given by the product of f sub x, which is 0, times the first component of my unit vector, which we found to be 2 over root 5, plus the partial derivative with respect to y, which was 1, times the second component of our unit vector, which was -1 over root 5. So in this case, we're just left with -1 over the square root of 5 as our directional derivative. So what this means is that this function, f of xy, if we start at the value of this function at the point -1, 0, and we move along the vector to -1, so we're increasing our x value at a rate of twice what y is being decreased by, then the corresponding change or rate of change in our function is a decrease by 1 over the square root of 5. So let's look at some other examples of directional derivatives. In this next problem, we've got something pretty similar to the last example. We want the directional derivative of f of xy at the point P, given by -1, 1, and moving in the direction of the point Q, which is 3, 2. So here we aren't initially given a vector that specifies the direction we're moving in, but we're told that we're moving from the point P in the direction of the point Q. So our direction vector is going to be the vector v, whose initial point is P and terminal point is Q. Now the components of this vector from point P to point Q would be 4, 1. So once we have the vector that indicates the direction in which we're moving, we need to normalize it. We need a unit vector that acts in this same direction. So again, to find a unit vector in the direction of v, we could take the vector v and divide by its magnitude. So here we have the vector 4, 1, and we're dividing by the square root of the sum of the squares, which would be square root of 17. So our first component is 4 over the square root of 17, and second component 1 over the square root of 17. Now, as with our last example, once we have our unit vector that specifies the direction of motion, we're going to need to find our partial derivatives of the function with respect to x and y. Here, the partial derivative with respect to x is 4y, and the partial derivative of our function with respect to y is 4x plus 2y. And we're interested in the value of our directional derivative at the point -1, 1. So let's evaluate these partial derivatives at our point of interest, negative 1, 1. So our partial derivative with respect to x is 4, and the partial derivative with respect to y is negative 2. Now, once we have these components, we're ready to apply our formula for the directional derivative of the function f in the direction of the unit vector u at the point negative 1, 1. So again, it's given by the partial derivative of f with respect to x, which was 4, times the first component of our unit vector, 4 over the square root of 17, plus the partial derivative with respect to y, which was negative 2, times the second component of our unit vector u, which was 1 over root 17. So we get 16 minus 2, or 14, over the square root of 17 for our directional derivative. Okay. Now the next thing that we're going to look at in this section is something called the gradient vector. So the gradient vector is a vector that is associated with any multivariable function. So let's start by defining it. In the case that we have a function of two variables, x and y, which is differentiable, we would define the gradient of that function as the vector function whose notation is the following. So the gradient vector is denoted by using this little upside down triangle. Sometimes this symbol is called nabla, or sometimes del, people will say. Or we could also use the notation grad f of x and y, grad being short for gradient here. And the gradient vector is defined as the vector whose components are the partial derivatives of our function with respect to x and with respect to y. So the gradient vector is a vector whose component functions are the partial derivatives of the function we were given. So really, any problem that's asking for a gradient vector of a function is just asking us to find its partial derivatives and put them into the components of a vector. So let's get a little practice with finding gradients. In this first example, we're asked to find the gradient of cosine 3x squared minus 2y squared. So to find our gradient, grad f or nabla f of xy, we would be looking at the vector function whose first component is the partial derivative with respect to x. So using the chain rule, here our partial derivative with respect to x is 6x times negative sine of 3x squared minus 2y squared. And our partial derivative with respect to y would be a positive 4y times sine of 3x squared minus 2y squared. And we would put those partial derivatives into the components of this vector, and this is what we call the gradient of that function. And we'll see throughout this course that there are many nice applications of the gradient vector. So now that we've worked with one of these, let's look at some other examples, get a little more practice. In this next problem, we're asked for the gradient of the following vector function. So again, grad f as a function of x and y will be the vector whose first component is the partial derivative with respect to x. So in this example, we're going to have to make use of the product and chain rules to get that partial derivative. So we start by differentiating this first factor x, which gives us a 1, times the second factor, x squared minus y squared to the 2/3 power. And then we add the factor x times the derivative of this second factor, which, using the chain rule, would be 2/3 times x squared minus y squared to the negative 1/3 power times the derivative of the inside with respect to x, which is 2x. And now for our second component, we're looking at the partial derivative of f with respect to y. So here, again, making use of the chain rule, we would have, for the derivative of the outer function, 2/3 x times x squared minus y squared to the negative 1/3 times the derivative of the inside with respect to y is a negative 2y. So we can simplify our answer a little bit here. Let's look at this first component. We have x squared minus y squared to the 2/3 plus 4/3 x times x squared minus y squared to the negative 1/3. And for our second component, we have a negative 4/3 xy times x squared minus y squared to the negative 1/3. And this would be our gradient vector, or gradient of that function. So let's look at another one. In our next example, we are asked for the gradient of the following function. So again, to find grad f of x and y, we're looking at the vector function, where our first component would be the partial derivative with respect to x. So here, using the chain rule, we're going to have e to the xy times the derivative of the inside with respect to x, would give us a factor of y out in front, plus the derivative of sine of a function is going to be cosine of that function, times the derivative of the inside with respect to x, gives us a factor of 2x out in front. And then our second component would be the partial derivative with respect to y. So similarly, we have x e to the xy plus 2 times cosine of x squared plus 2y. So this would be the gradient of that vector function. So we've got a few examples of finding the gradient of a function. So let's start talking about some of the applications. The first application that we'll consider is in calculating the directional derivative of a function. So we have an alternative formula for a directional derivative, which involves the gradient of our function. This is sometimes called the gradient formula for that directional derivative. And it says if we have a differentiable function f of two variables x and y, then the directional derivative of f in the direction of u at xy could be given by the dot product of the gradient of f with the unit vector u. And let's see why that would in fact be true. So here, if we're thinking about the dot product of grad f and u, well, grad f is the vector whose components are the partial derivatives of f with respect to x and y, and we're taking the dot product of that with a unit vector u, whose components, let's say, are a and b. Now, using the definition of the dot product, we would be looking at the product of the first components, that is f sub x times a, and then we would add the product of the second components, partial derivative with respect to y times b. And this is the exact same formula that we were already using to find the directional derivative. So now we can write it a little more concisely in terms of the gradient vector and a dot product. So let's look at some examples of finding a directional derivative of a function making use of this gradient formula. So in our next example, we're asked for a directional derivative of the function at the point 2, 3 in the direction of this vector v, whose components are negative 2, 1. So as always for these directional derivative problems, our first step is to find a unit vector specifying the direction of motion. So here we're going to take our vector v and divide through by its magnitude. So here v was the vector negative 2, 1, and we're dividing by its magnitude, which is the square root of 4 plus 1. So here our directional, or our unit vector is negative 2 over the square root of 5 and 1 over the square root of 5. So for any of these problems, we always want to start by finding that unit vector. And the next thing we need to find would either be the partial derivatives of our function or the gradient vector, which contains the partial derivatives of our function. So here, let's look at grad f at a general point xy. So we're looking at the vector whose first component is the partial derivative of f with respect to x, which is 3x squared y squared. And our partial derivative with respect to y is 2x cubed times y. Now we're interested in the value of our directional derivative at the point 2, 3. So let's evaluate our gradient, grad f, at that point. So here, plugging in 2 for x, 3 for y, let's see, we have for our first component 3 times 4, or 12 times 3 squared is 9. And then for our second component, we have 2 times 2 cubed is 16 times y, which is 3. So this reduces to 108 and 48. And for our directional derivative of this function f at the point 2, 3 in the direction of the unit vector u, we're going to look at the dot product of the gradient vector at the point 2, 3 with our unit vector u. So multiplying the first components of these vectors, we're going to have negative 216 over the square root of 5. And then we're adding the product of the second components, 48 and 1 over the square root of 5, which gives us 48 over root 5, which reduces to, let's see, 1 negative 168 over root 5. Okay. So we can find the directional derivative in much the same way that we were doing earlier, but instead of finding the partial derivatives of f with respect to x and y separately, here we can now combine those partial derivatives as a single expression using the gradient vector. So let's look at another one of these. In our next example, again, we are asked for the directional derivative of this function at the point P, given by 2, 2, and moving in the direction of the point Q, 1, negative 1. So again, we're going to start by finding here a vector that moves between these 2 points, that is from the point P in the direction of the point Q. So for our direction vector v, we could take the vector from point P to point Q, whose components are negative 1, negative 3. And we need to now find a unit vector in the direction of v. So we're going to call this vector u, which is found by taking v and dividing through by its magnitude. So here we have -1, -3, divided by the square root of 1 plus 9. So we have the vector -1 over root 10 and -3 over root 10. All right. Now, the next thing we need to find is the gradient of f at a general point xy. So here our first component would be the partial derivative with respect to x. So we have e to the x minus y power times 1 for the derivative of the inside with respect to x. And then e to the x minus y times a -1 for the partial derivative with respect to y. And we're interested in the value of our directional derivative at the point 2, 2. So let's evaluate our gradient at that point, which would give us e to the 0 or 1 and -1. So once we have these components, we're now ready to find our directional derivative of the function f at the point 2, 2 in the direction of u. Again, we find this by taking the dot product of our gradient vector at the point 2, 2 with our unit vector. So here we have a -1 over the square root of 10 plus 3 over square root of 10, or 2 over the square root of 10. All right. Now, in the next part of this section, we're going to extend what we've been working with, that is the concept of a gradient or directional derivative, to functions of 3 variables. And then, of course, we could extend these concepts to functions of 4 or more variables. So let's suppose that we're working with a function of 3 variables, x, y, and z. Now, the gradient of such a function is denoted as nabla f of xyz, or grad f of xyz, and it would be the 3-dimensional vector function whose first component would be the partial derivative with respect to x, second component is the partial derivative with respect to y, and our third component is the partial derivative with respect to z. And in the same way that we were finding a directional derivative of a function of 2 variables at a point, we could define the directional derivative of our function f at a point x naught, y naught, z naught in the direction of a unit vector u as the dot product of our gradient vector with the unit vector specifying our direction evaluated at the point x naught, y naught, z naught. So we have a natural extension of the gradient or directional derivative to functions of 3 or more variables. So let's consider the following example. We are asked for the directional derivative of the square root of xyz at the point 2, 4, 2, acting in the direction of the vector v given as 4, 2, -4. So as always, with these directional derivative problems, our first step is going to be to find a unit vector in the direction of v. So here our vector was 4, 2, -4, and its magnitude is then the square root of 16 plus 4 plus 16, which is square root of 36, or 6, as our denominator. So our unit vector is then the vector 4 over 6, or 2/3, 2 over 6, which is 1/3, and -4 over 6, or -2/3. And we also need to find our gradient vector, grad f at a point x, y, z. Now, the first component of our gradient vector is the partial derivative of our function with respect to x. Now let's look back at our function. It's the square root of x times y times z. Now the derivative of the square root of some function is 1 over twice the square root of that same function, x times y times z. And then using the chain rule, we're supposed to multiply by the derivative of the inner function with respect to x for this first component, which would give us y times z. And for the second component, again, the derivative of our outer function would be 1 over twice the square root of x times y times z, multiplying by the derivative of the inner function with respect to y, we have x times z. And then for our last component, we have 1 over twice the square root of x, y, z, times the derivative of the inside with respect to z leaves us x times y. And we're interested in the value of this gradient at the point 2, 4, 2. So let's evaluate our gradient vector at this point. So for our first component, we have a numerator of y times z, which is 8, divided by 2 times the square root of x times y times z. Now x, y, z here gives us 16, so the square root of that would be 4. For our second component, our numerator is xz, which is 4, divided by, again, 2 times the square root of 4, or square root of 16, which is 4. And then for our last component, we have x times y, which is 8 over 2 times 4. So we're left with the vector 1, 1/2, 1. And now our directional derivative of the function f at the point 2, 4, 2, acting in the direction of u, is the dot product of our gradient at the point 2, 4, 2 with the unit vector u. So here, let's see what we have. We have for our first component, 1 times 2/3 plus 1/2 times 1/3 is 1/6, and then plus 1 times negative 2/3 is minus 2/3. So our plus minus 2/3 will cancel, and we're left with 1/6 for this directional derivative. Okay. Now in the last part of this section, we're going to talk about some applications of the gradient vector. Now, the first application that we'll talk about, other than using it to find a directional derivative, is the so-called maximal property of the gradient. So let's explore what exactly this property of the gradient specifies. So let's say that we have a function f. It could be a function of 2 or 3 variables. Then the maximum value of the directional derivative of our function at a point, say specified as x, it might be, say, xy or xyz, depending on whether we're working with a function of 2 or 3 variables, is given by the magnitude of the gradient function at that point x. So the maximum rate of change of our function at some point is given by the magnitude of the gradient vector of the function at that point, and the direction in which the maximum rate of change occurs, so the direction that we need to move to achieve the greatest rate of change for our function is in the direction of the gradient vector itself. So this has some very nice applications if we're wanting to most rapidly maximize or most rapidly minimize a given quantity. We would look at moving in the direction of the gradient vector, and the greatest rate of change, or the greatest directional derivative from any point, is then given by the magnitude of that gradient vector. So let's look at an example making use of this. In this next problem, we're given a function f in terms of 3 variables, and we're asked to find the rate of change of that function at the point 2, 2, 7 in the direction of the vector v, 1, 1, negative 1. So this is a problem in finding a directional derivative. So as always, our first step would be to find a unit vector u in the direction of v. So here our vector v was the vector 1, 1, negative 1, and the magnitude of that vector is the square root of 1 plus 1 plus 1. So here we have our unit vector 1 over root 3, 1 over root 3, negative 1 over root 3. And the gradient of f at some point x, y, z is given by the vector whose first component would be our derivative with respect to x. In this case, 6x minus 5y plus yz. Our second component would be the derivative of f with respect to y. So here, negative 5x plus xz. And our last component would be the derivative with respect to z, which gives us just x times y. And we're interested in the value of the directional derivative at the point 2, 2, 7. So let's evaluate the gradient at this point. So here for our first component, we're going to have 12 minus 10 plus y times z, which is 14. For our second component, we'll have negative 10 plus x times z, which is 14, and x times y, which is 4. So this reduces to, let's see, 16, 4, and 4. So for our directional derivative in the direction of u of our function f at the point 2, 2, 7, we will have a 16 over square root of 3 plus 4 over square root of 3 minus 4 over square root of 3 as the dot product of this gradient vector with our unit vector. So we see here that our plus minus 4 over the square root of 3 cancel, and we're left with 16 over root 3. Now, in part B of this question, let's say that from this point, 2, 2, 7, we want to know how could we most rapidly make an increase or decrease in the value of our function. So in part B, we're asking in which direction does f change most rapidly, and also what is the maximum rate of change. Now this theorem that we had just looked at said that the maximum rate of change occurs in the direction of our gradient vector. So here we are going to have the max rate of change in the direction of our gradient vector, grad f, at the indicated point, 2, 2, 7, which from part A of the problem we found to be 16, 4, 4. And it occurs, or this is the direction in which we have the maximum rate of change. And the actual maximum rate of change is given by the magnitude of the gradient vector. So here the maximum rate of change is the magnitude of our gradient evaluated at the point 227. So here we would have the square root of 16 squared plus 4 squared plus 4 squared. So here we have the square root of 16 squared plus 16 plus 16. If we factor out a 16, square root of 16 is then 4, and we're left with 16 plus 2 under the radical. So that would be root 18, or 2 times 9. So I think in the end we're left with 12 square root of 2 as the maximum rate of change, and the direction in which it occurs is in the direction of this vector. Okay, so one nice application of the gradient here is that it can tell us in which direction we should move to achieve the greatest rate of change of our function at an indicated point. Now, the last application of the gradient vector, which we'll talk about in this section, is in determining the tangent plane to a surface which may not be the graph of a function. So in our section 4.4 material, we saw how to find the equation of the tangent plane to the graph of a function at a point. But not every surface is the graph of a function. So examples of surfaces that would not be the graphs of functions might be some quadric surfaces, say spheres, hyperboloids, elliptic paraboloids, things like these. So let's consider a surface S that is the graph of an equation f of xyz equals to some constant k. So this sort of surface, recall, is what's called a level surface of a function of 3 variables. So level surfaces, recall, are the surfaces you get by setting your function of 3 variables equal to different constants. So here, let's say we have our surface shown in blue down here, S, and we're going to choose a point x0, y0, z0 on that surface. And we're going to take C to be any curve which lies on our surface and passes through the point P. So let's take some sample curve passing through that point which lies on our surface. Okay. Now, the gradient vector of this function, f, which is my level surface, or is defining my level surface, is normal to the tangent plane to the surface at that point. So if we were to consider our normal vector, our gradient vector of this function f evaluated at x0, y0, z0, this is a normal vector for the tangent plane to my surface at the point P. So in other words, if I want to find the tangent plane to a level surface, well, I need a normal vector to find the equation of that plane. And we're finding that this gradient vector, grad f, is normal to the tangent plane at any given point on a level surface. So we define for a level surface S, defined by some function f, for a point x naught, y naught, z naught, which lies on that surface, the gradient vector is normal to the tangent plane to the surface S at the indicated point. Now, another object of interest for a surface is something called the normal line to our surface at a point. So how are we going to define this? Well, we'll define the normal line as the line which passes through the point x naught, y naught, z naught. So it's passing through my point P, and it is specified as moving in the direction of the gradient of f, this normal vector to our surface. So if I consider the line which passes through my point P and lies orthogonal to the surface, or normal to that tangent plane, this line is what is called the normal line. To our surface at the point x naught, y naught, z naught. So in our last example, we are asked to find equations for both the tangent plane and the normal line to the surface defined by the following equation at the point 2, 1, negative 1. So here, the equation that is defining our surface cannot be easily solved for z as a function of x and y. It's possible to solve for z, but it's a little tedious to do it here. So here we have a level surface, which is defined by setting a function of 3 variables, f of x, y, z, which in this example is x squared y plus y squared z plus xz squared, equal to a constant value of 5. So this is a level surface. And we know that the gradient vector for this function is normal to our tangent plane. So if I wanted to find the equation of my tangent plane, I would need to find that normal vector. So let's start by finding grad f in terms of x, y, and z. So here our first component, the derivative with respect to x, is 2xy plus z squared. Our second component would be x squared plus 2yz. And our third component is y squared plus 2xz. And we're interested in finding the tangent plane to this surface at a specific point, 2, 1, negative 1. So let's evaluate our gradient vector at that point. So here we have 2 times x times y would give us 4, plus z squared is 1. X squared is 4, plus 2 times y times z would be negative 2. And then y squared is 1, plus 2 times x times z would be minus 4. So we're left with 5, 2, negative 3. Now this vector, which we've just found, is normal to our tangent plane. So in order to find the equation of a plane passing through a given point with a given normal vector, we would make use of the theorem that we saw in one of our early, I believe, chapter 2, for the equation of a plane. We would take the first component of our normal vector, 5, times x minus the x coordinate for the point that our plane passes through, which was 2. plus the second component of our normal vector, 2, times y minus the y-coordinate for the point that we're passing through, and then plus the third component of our normal vector times z minus a -1, would give us z plus 1, and we're setting that equal to 0. So simplifying a little bit, for the equation of our plane, we have 5x minus 10 plus 2y minus 2 minus 3z minus 3 is 0, or rewriting this in standard form, we have 5x plus 2y minus 3z. Let's see, minus 15 is 0, so we could add 15 to both sides, and we have the equation of our tangent plane in standard form. Now, this problem also asks us to find the normal line to this surface at the point 2, 1, 1. So for our normal line, we're looking for the line which is passing through the point 2, 1, -1, and is in the direction of this normal vector. So remember, to define a line in 3 dimensions, we need parametric equations for our line. So we are going to have an equation for x, y, and z. And our x equation would be given by the x-coordinate for our point, which was 2, plus the first component of our direction vector, which was 5, times t. Our equation for y is given by the y-coordinate for our point, 1, plus the second component of our normal vector, 2, times t. And z is given by the z component of our point, -1, minus 3 times t. So these would be parametric equations for the normal line to the